Hi, me again. Welcome to the third installment of hydrodynamics. We've learned the basic principles, law of continuity and Bernoulli's equation, and so we're going to apply it numerically and conceptually to a few other problems before we let you loose on your own. So here's a good one. So I think you know, maybe you don't, that when a tornado comes around, and it doesn't happen often around here, but if it comes around and it's going to come close to a house, people say, well, we should open the windows, all right, which might seem counterintuitive. And so we're going to look at a problem that helps maybe explain that, why opening the windows might protect your house more. This is assuming you don't have a direct hit. The tornado comes right through your house, then it's gone. However, if it comes by and you have very, very high winds because of that tornado, it can rip the roof off of your house because of a Bernoulli effect. And opening the windows can help prevent that. It's not a guarantee. So in this case, we have a modest 30 meter per second wind. So that's, 70 miles per hour. And let's say it's fairly sustained. It's not just the outflow from a cloud that might knock over trees, but this is sustained. And we want to know what is the net pressure on the roof if the windows are closed. And by closing the window, and we're assuming the air in your house is not moving. So we want to set up two regions. In this case, region 1 is going to be outside, just outside your roof, and region 2 is inside where there is air. Now, let's think about what the situation is before the wind even blows. Before the wind even blows, there is atmospheric pressure, right? And there's atmospheric pressure in there, and they're the same. Okay, so what this problem is suggesting is when the wind blows, especially over the roof, there's going to be a pressure difference there. Well, that's not immediately obvious why that should occur conceptually, but if you look at Bernoulli's equation, it kind of makes sense. Because Bernoulli's equation says pressure in one region plus the kinetic pressure, I get tired of writing this, I'm not even going to put the subscripts there, plus any static pressure due to some change in height has to remain constant. Okay, so if there's no wind blowing, then the P here has to equal the P over there. There's no difference in height in the air, so to speak, and if there's no air flowing in or out of the house, then the pressures are the same. However, if there is a region where air is flowing over and there's another region where there isn't, then those are not equal. And so to satisfy this whole relationship, that means there has to be a pressure difference between inside and outside to balance the equation. Okay, so in this problem, this aspect is not an issue. There is no difference in height, so to speak. Okay, because we're just looking on the inside of the roof versus the outside of the roof. They're at the same height. So this now becomes our pressure difference. That's what we're trying to solve for. So I'm just going to call that delta P is equal to the difference in the kinetic pressure. And since the speed on the inside of a house is 0, it's just 1/2 rho times V1 squared. Okay, so what rho are we talking about? Well, we're talking about air. The rho of air, don't remember, this I think came up way early on in the unit, is 1.29 kilograms per cubic meter. Remember, water is 1,000, so this is very, very low. So if I apply Bernoulli's equation to this, it doesn't seem like it's a big deal. I put in 30 squared. I get 580 roughly pascals. Okay, remember, atmospheric pressure is 101,000 pascals, but the pressure difference when there's no wind flow is 0 because inside and outside are the same. So this is a pressure difference. 580 pascals doesn't seem like a lot, but if we translate to a force, where the force on the roof, the net force on the roof, because of that fluid flow, and that net pressure, remember, this area, let's be clear, if I haven't made it so, this is the area of low pressure, because there's that fluid flow there, low P. So the inside is high P. So if we keep the windows closed and maintain that pressure difference, that's going to put an outward force on that roof, and that outward force is going to be that pressure times the area of the roof. And so even though it doesn't seem like a lot of pressure, let's say our area is, let's say it's a 10 meter by 10 meter roof. That's not outrageous. Okay, so heck, let's make our, that's 10 meters by 10 meters is, let's say, 100 square meters, multiply that, you've got, right, did I do that right? 580, add 2 zeros. Okay, so we're talking now approaching 50 to 100,000 newtons. You know, if we change our area by a little bit, that's going to be significant. So that can be an issue. So by opening the windows, any pressure difference will allow air to flow out of it, so it doesn't maintain that, and it puts a little less stress on your roof. All right, number 3 is a pretty important problem because it puts a lot of these ideas together, all aspects of that. So this is water circulating through a house where it can rise up from one floor to another. Okay, and first of all, the water is pumped, right? There's some pump. It could be from a water tower or an external pump. It's pumped with a speed, a certain speed of a certain diameter, and there's a gauge pressure at one floor. And then on the second floor, which is 5 meters above, we have the pipes constrict to 2.6 centimeters per second. And then ultimately, what we want to figure out is B. What is the pressure at the second floor? Okay, in order to get the pressure at the second floor, we need to figure out the speed of the water at the second floor. So if we were to draw a very crude schematic of what's going on, okay, we've got a large area, we've got a small area, we've risen in height. And when we've got a pressure difference, there's a P1, there's a P2, and we're assuming they're going to be at different pressures. What I want you to understand is as the water rises, it's not going to slow down because of that pressure here. It's going to help maintain speed. Any speed change is going to occur because of a constriction. And so when we ask what's the speed of the water on the second floor, because of the constriction in pipe, that screams the law of continuity. In other words, A1V1 at the bottom has to equal A2V2 at the top. So V2 at the top is simply equal V1 at the bottom times the ratio of the areas. And in this case, the areas are going to be pi r squared. Now we're given diameters. Yuck. So I'm going to do pi. Actually, the pi's are going to cancel out because it's that. So it's just 1/4. That's half the diameter squared is the radius, right? Times 2 points. Let's see, is pump with the speed. 2.6. Oh, I always get that mixed up. My bad. Okay, that's going to be the 4.0 centimeters. I don't have to convert to meters because I'm going to compare centimeters to meters to 2.6 centimeters squared. Okay, and if I did it right, which I probably didn't, is 1.18 meters per second. In fact, I don't even need this. I'm sorry. We're going to have half the ratio. They're going to cancel out anyway, so it's just the ratio of the diameters. Okay, now we can ask what's the pressure at the top. And the pressure at the top can be found by Bernoulli's equation. So what we're going to say, I'm going to solve for delta P, and then I'll use that to find the other pressure. So delta P is simply going to be equal to 1/2 rho, the difference in speeds between the two floors, and then plus whatever happens due to the change in height. Okay, so there's our kinetic part, there's our potential part. So what we want to do is I want to do each of these individually because I want you to contrast these. So if I do 1/2 times 1,000, that's the water's density, times what was given as, let's see, 1.18 squared, right? That was at the top floor, minus 0.5 squared. I will get, oh, I probably did, yeah, here we go. No, I didn't do them individually. Plus 1,000 times 9.8 times the difference in height, and our difference in height is 5 meters. I think it's easy to see that this term right here is going to dwarf this term. This term is going to be very small compared to this. Anyway, if I solve for that delta P, I'm going to get 49,500 pascals. Okay, so that's the difference in pressure between the two, but we didn't ask for that. We asked what is the pressure at 2. Okay, so the pressure at 2 is equal to the pressure at 1 plus whatever difference in pressure there is. So what's the pressure at 1? Well, you're told that there's a gauge pressure of 3 atmospheres. Okay, so that pressure, we can keep it as 3 atmospheres is 303,000 pascals plus the 49,500. So for all intents and purposes, it's about 350,000 kilopascals. Now I want to point something out because I know this confuses students. The P2 is, so what we have here is a gauge pressure. If I want the absolute pressure, then I would add on an atmospheric. But there's also an atmospheric on this term, so they canceled out, so they didn't come into play on this one. But this is a gauge pressure. If we wanted the absolute pressure, then we'd have to add in atmospheric pressure there. Okay, so let's look at some other problems while I still have some time left. All right, applications. Here's a cute one. Prairie dogs. I don't know if you've ever seen prairie dogs out west before. They are notoriously hard to take pictures of because as soon as you look at them, they pop into their hole. Any burrowing animal, if you're going to live underground, has to have at least 2 points of entry or egress. If he didn't, what would happen is the air inside that, let's say it just stopped right there, this was blocked up, would stagnate, okay? And they would suffocate because as they're taking in the oxygen and all that, that CO2 that they're breathing is denser than air, and so it's going to build up in there. And so any hole, especially the classic ones are the groundhog holes, is they have an entrance where there is a slight elevation difference between one opening and another. And because of that slight elevation difference, the velocity over this hole here is going to be a little greater than velocity there. So generally the wind velocity is higher as you go up in elevation to a certain limit. So what's the consequence of that? Well, this is where Bernoulli's law comes into play. We learned from the law of continuity that areas of high velocity correspond to low pressure. So in other words, if this is PA and this is PB, we can see, that PA has to be less than PB. So what's the big deal in that? Well, we create a pressure difference, which is going to cause air to flow through that. So you get some circulation created by that, and so that constantly refreshes the air. And something similar happens with a airfoil or wings. Okay, so if this is a profile of a wing and you have these air streams flowing over it, because they're constricted here because of the shape of the top of the wing versus here, that constriction implies, for reasons we'll talk about later, that the V, I'll call it top, versus V bottom, implies that V top is greater than, V bottom. Even though the plane is moving at a certain velocity here, this shape alters the speed over there. And so if V top is greater than V bottom, that means the pressure at the top has to be less than the pressure at the bottom. So if there's a higher pressure here, so this is high P, and this is a low P because of that speed, we're going to get a pressure difference that's up. And that, in part, helps lift the plane up on the wings. That's not the only thing. Another thing that a wing does that's, I think I've read, is just as important, if not more important, is the wing, especially if it's pitched, more at an angle, okay, the angle of attack, and that's not a very good drawing, so that it deflects the air down. By pushing the air down, the air has to push up, so that also helps. Anyway, so that's how you can use Bernoulli's principle to explain lift on a plane, at least partially. The last thing I want to show you before I run out of time here is a perfume bottle, where you squeeze this bulb in, and then you get the perfume or whatever liquid in there to come out in a fine mist. So why does that work? Well, again, Bernoulli's a principle. Is basically what you do is when you squeeze it right here, you send air moving at a high velocity. So in this little tube that's connected to the liquid, where there's no air moving, as the air pushes past, it creates a low pressure zone. So we have a low pressure zone right over this. We have the atmospheric pressure right here in the bottle, so it pushes it up, and then you have a little atomizer to make it a fine spray. So that's how little squeeze bulbs can create fine sprays, is basically moving air creates a low pressure zone, and I'll demonstrate that in class.